Hello and welcome back. This is the, Lecture 6 for the Systems 556, 750 course, Simulating Neurobiological Systems, taught at the University of Waterloo in the fall of 2021. And today we are going to talk about recurrent dynamics. What happens when you connect neurons back to themselves? What do I mean by that? So far in this course, we have had inputs that we can feed into groups of neurons, and then we can decode output from those and feed them into another group of neurons. And the whole point of the last sort of lectures is that when you make these sorts of connections from this one group of neurons to the next group of neurons, you can find the connections that will approximate some function. What we're going to do today is sort of say, well, hold on a second, what happens when you do that from a group of neurons back to itself? Why would I want to do that? Well, one aspect is just simply that, well, neurons in biological systems do this. You tend not in biological systems to have inputs going to one group of neurons, going to another group of neurons, going to another group of neurons in this sort of very feed-forward manner. That's very common in artificial neural networks. It's not particularly common in biology. Instead, we tend to have lots of connections back to themselves, connections from one group, maybe from one group to another group, and then from that group back to the first group. That sort of thing seems to happen all the time. We would like to understand it. And in particular, we really want to try to figure out just what does that behavior end up doing. The punchline is going to be that this is going to give us a new type of thing that we can generate with neural networks, a new sorts of computations that we couldn't do with purely feed-forward. And this is sort of widely known in the artificial neural network community. If you want your output to be more than just a function of your current input, right? So let me try that again. In this sort of feed-forward system, whatever the output is from my network is pretty much just going to be some function of whatever my original input was. Right? There's no way that this purely feed-forward system can have any sort of long-term memory. And so traditionally what will happen in artificial neural networks is if people want outputs to be a function of not only the current input, but also previous inputs, then you're going to need to start putting in some sort of recurrent connections. Okay. So that's going to be our hope, is that by adding in these recurrent connections, now we're going to be able to do something that is more than just some function of my input. Okay. But we'd like to sort of mathematically characterize exactly what it is that we gain out of all this. So that's going to be our goal in this lecture. One slight complication, though, is going to come up. And this is just more of a software design complication and not any sort of complication theoretically. Because we've already discussed how to form, like, the basic trick that we're going to do is we're going to do exactly what we did for making these connection weights from one group of neurons to the next. Solve for decoders, multiply the decoders by the encoders, that gives us our connection weight matrix. But we're just going to do that from one group of neurons back to itself. We're just going to generate this connection weight matrix the same way we generated the feed-forward connection weight matrix. So we're not going to be introducing any sort of new ways of connecting anything or sort of any sort of new conceptual things. We're just going to be looking at, well, what are the consequences of doing exactly what we've already been doing, but doing it in a recurrent context. However, sorry about that. However, we've got a slight software problem here. And the software problem is, as we've been sort of in the assignments in this course, we've been implementing this code where you sort of, okay, here's an input signal, feed it into a group of neurons, get some spikes, take the spikes, multiply them by some connection weights, multiply them by some low-pass filter, convolve them with some low-pass filter. That process depending on how you've implemented that software, it might be a real pain to do this in the recurrent context. When we were doing these feed-forward things, we could get away with sort of, okay, I'm just going to generate all of my input signal, then I'm going to find out what this group of neurons does over time, then I'm going to find out, multiply those spikes by some connection weight matrix. That's going to give me my inputs to these neurons. Now I can run these neurons over time. I could, in my software, I could do it part by part. And indeed, that's how people are going to be doing things for assignments 2 and 3. But that's not going to work the moment I start getting into this context. In this context, just from the software side, I've got to make sure that I'm sort of like simulating one time step for these neurons, figuring out what the outputs are, multiplying those outputs by that connection weight matrix, feeding that back in, and then doing one more time step. And I might have this happen for multiple layers, and it just gets annoying code. And so there's no sort of, it's not conceptually interesting code, it's just annoying. Let me rephrase that. It's not interesting in terms of the sorts of things we're trying to teach in this course. There's some really cool underlying software design stuff in order to do that sort of work efficiently, but it's just not the topic of this course. So we don't want to force people to implement all that sort of complex software. So this is going to be the point in the course where we're going to start allowing people to start using pre-built software. And indeed, the particular software toolkit that we've developed here at the University of Waterloo, which is called Nango. So I'm going to start this lecture. We're just going to do a little bit of a quick introduction to Nango, to defining these sorts of models, just because that's going to let us sort of interact with or try out the different things that we want to talk about in this recurrent context. All right, so I'm going to start with that. What are we going to do? So there is this Python software toolkit called Nango that we've developed. You can install it by saying pip install Nango. As long as you've got Python installed. Oh, of course, I already have it installed on this system. If you have if you have Nango installed, then it is going to be a nice little Python package. Let's pull up. So we'll say this Nango example. Yes. And we'll just go ahead. Oops. That plot lib inline. Let's just make sure that I can do some plotting. Oops, sorry. Import numpy as a p, and import Nango. All right. So this import Nango, so this is all just plotting and numpy. I figure I might use those at some point. Importing Nango, that's what's giving access to the Nango library. And this is just a toolkit basically to do the sort of defining of neural networks that you've already been doing in the course. Okay. And so I just want to do a few quick examples of how you might, of how we're sort of packaging up the various different things you're already implementing in this course in Nango. The way Nango works is the first thing I do is I create a network. A network is just a container for a bunch of components. Okay, so it's just an organizational thing. You can have networks inside networks inside networks. They don't actually do anything about the model. They're just for organizational purposes. And I'm going to give this command. This is basically saying that anything I put inside this with block, these are all things that will get added to the network that I've just defined. Okay. So it's just anything that I now go ahead and create will automatically get added to that network. So I might want to create a group of neurons. Terminology for a group of neurons, we call it an ensemble in Nango. So I'm just going to create a group of neurons ensemble. And there's a whole bunch of things we can specify about this group of neurons. All the various different properties, all the various different things that you end up specifying when you're creating groups of neurons, but there's two that are always required. One of them is the number of neurons, fine, and the other one is the dimensionality. So these 100 neurons, what's the dimensionality of the space that they're representing? So this 100 neurons is representing some variable x. Is x one-dimensional, two-dimensional, three-dimensional? Yeah, we're going to say it's one-dimensional for now. Okay. So that always has to be specified. It's now going to go ahead and say, okay, well, now what, I'm going to need encoders for these neurons. I haven't specified what encoders to use, so it's going to randomly generate them. I haven't specified what firing rates, what intercepts. We'll play with those in a moment. I'll just give examples of that, but all of those would be things you can adjust there. One sort of important one is what neuron model are we using? And the default is a leaky integrate and fire neuron model. Okay. But there's lots of other options. I can use a rectified linear. I can use a sigmoid neuron. I can use a leaky integrate and fire rate mode neuron. So the same sorts of possibilities that we've been seeing in the course. We'll be sticking with the leaky integrate and fire neuron. All right. So now I've got a bunch of neurons. I might want to feed some input to those neurons. Okay. If I want to feed some sort of input to those neurons, I'm going to create what we're going to call a stimulus. Anything that's not neurons in Nengo is going to be called a node. And what you can do with a node is you can say, all right, well, one simple thing I can do is, all right, let's just feed in the value 0 all the time. It's just a really boring input, but we can go ahead and do that. Yeah, that's a really boring input. Let's pick something a little bit more complicated. I can define my stimulus, some function over time, and maybe it's just, I don't know, a sine wave. Okay, so there's a function that is just a sine wave, and I'm just going to give that to it. So now this is going to be a node that is going to be using this function. T is the time of the simulation. The time of the simulation is going to start at 0. It's in units of seconds. We're going to go ahead and make that node. And now I would like to connect that node to this ensemble. That is, we're going to say there's a connection from the stimulus to the ensemble. Now, every time we make connections, there's the opportunity to put in a synapse model. Okay? So again, this is exactly the various synapses that we were looking at in the course and in the assignment, where, okay, whenever there's a spike, you can put in some sort of low-pass filter. You can do that even when there aren't spikes. That's all fine. But anytime we have a connection in Nengo, there is going to be some option of saying, hey, there can be a low-pass filter here, or some other synapse model. You can do any linear time invariant synapse model. But the default, the simplest default, actually the default is a 5 millisecond low-pass filter. So for the synapse parameter, you can specify a full complicated, more complicated function. Most of the time we're getting away with just low-pass filter synapses, so just as a convenience, we can just simply say, oh, all right, fine, 5 millisecond. If I just specify 5 milliseconds, that's going to be a 5 millisecond low-pass filter synapse, and that is the default. In this particular case, I just want to feed in input. We're just going to put no synapse whatsoever there. All right, so fine, I've defined an input. I've got some neurons. That seems sufficient. how do I actually go ahead and run this model? Well, all of this sort of defining of a model doesn't actually sort of create anything. We still have, if I run this code right now, it's like, okay, fine, you ran that. It still hasn't bothered actually generating the encoders or solving for decoders or doing any of those sorts of things. It's just sort of, you've just specified, this is the model that I want. If I want to actually sit down and say, cool, all right, now generate those encoders, find the gains, find the biases, all of the sort of steps that you've done in the assignments, what we do is we produce a simulator object and we pass into it the model. Okay. And then with that simulator, now I can run the simulation. And I can say, all right, please run this for, I don't know, 10 seconds. Now I can run the model, and it goes ahead and does things. So there's two phases. There's this building phase, that's when it's generating all the encoders, finding the gains and the biases, solving for decoders, doing all that math that you do just up front once, and then it runs the simulation for 10 seconds. Okay. But, I just ran the simulation. I didn't. Now, how do I plot anything out of that? It'd be really, I mean, it ran it, great. How do I get data out of this simulation? The way this is organized is you need to specify what data you want to record. So, for example, I might want to record what that stimulus was. Right? And we call these probes. So the probes are indicating what things I want to record. So, I don't know, I might have a probe of the stimulus, and I say that's a Nango probe, and I say, what thing do I want to record from? I want to record the stimulus. Okay. All right, I'll run that again. Yay, good. Now that I have this probe object, now I can go ahead and plot things about it. So I can get access to the, I can get the data for that probe, right, just by doing that. That's the big matrix. That just gives me a big matrix that is the data recorded from that probe. I probably want to plot it. Plot. Yay. All right, there's some plots. As a convenience, I probably, this x-axis, okay, what's going on with this x-axis? There's 10,000 elements in this x-axis. I ran it for 10 seconds. So when the simulation ran, there was some time step internally. You can actually specify that here. The default time step is 1 millisecond. So that's why when we ran it for 10 seconds, I got out 10,000 data points. As a convenience function, when I do this plotting, I can say, look, I want my x-axis to be in seconds, and just go figure out what it's supposed to be. Right? And that's sim.tRange, the time range. We can call that on a simulator. That'll give me the right elements to pass in as my x-axis. My plotting. Now my x-axis is in seconds. Right, my y-axis. Yay, there's my little sine wave that's being fed in. Okay, so I've recorded data from the node. I'd like to also record data from the neurons. Right. So, one thing I can do is actually get at the raw neurons themselves. And that's, I probe A neurons. Okay, so this A object here, I can refer to, please give me the data from the neurons themselves from that A object, from that A ensemble. Run that. Whoop. And now what am I going to get out of that? Well, this sim.data probe neurons is a big giant matrix with zeros and 1000s. The reasons they're 1000s is everything in Nango we try to keep in SI units. And so the units for spikes would be hertz. If you have a time step of 1 millisecond and the neuron spikes once in 1 milliseconds, that's a firing rate of 1,000 hertz. So that's why we get zeros and 1,000s in here. Similar reasoning as to why you did a similar thing in your assignments. But we have this data. We now do whatever we want with it. One common thing that I might want to do is plot spike rasters out of that. There's a variety of different ways of doing that sort of plotting. You could do, you could do a plot IM show of this. Aspect equals auto. Yay. Oops, and it's the transpose. All right. So that's that data. Okay, you can sort of see over time. So each row here is a different neuron, and the input was changing over time. This is, that's one way you could maybe plot that. I find that a little ugly. So there is also a built-in convenience function. Utils plot lib raster plot, and you give it the c.t range, and you give it the same object. Oh, whoops, helps if I actually import that. Yeah. And fine, so then we're actually getting nice, reasonable axes. Again, each row is a different neuron. And I might do something like, let's zoom in on that a little bit because it's a little hard to see. 0 to 1. There we go. So now I've zoomed in on it a little bit, and you can see the individual spikes on each of these neurons. Maybe we'll make it a little bigger. Here, big size equals, I don't know. There we are. Okay. So we can get access to these low-level sort of, here's the spikes, we can get the data coming out of the system. More interesting thing, though, is most of the time I'm not interested in what the low-level spiking detail is. I want to know what value is being encoded in the spiking activity. That's the whole point of the neural engineering framework, is we would really like to work with, well, what's being represented, rather than the low-level spikes. So, of course, there's another probe that will do that. If I just say probe A, it assumes that really what I want to do is what's the value encoded in A. So that means find the identity decoder, and plot me and just record that data instead. Okay, so I'll go ahead and run that. And now I can do plot and sim.data probe A. So that's my probe, and this is going to look really bad. Okay, well, we've got okay, why is it so horrible? I mean, it's clearly doing sort of what I want. Let me plot on top of that. For comparison, I can say what the input was. Stimulus. There we go. On top of that, let's make it black just so it's a little bit more visible. Yay, so there's my input. The blue fuzzy line, that was my output. This looks like a really bad decoder. Why is this a really bad decoder? Well, the default for probes is not to put a filter on. Most of the time when I want to decode data, though, it would be I want to decode the data with a filter. So we're going to specify that. We're going to say, all right, give me a 10 millisecond low pass filter. And again, every spike is going to get passed through the 10 millisecond low pass filter as part of the decoding process. Okay. And there we are. It's now doing a pretty good job of encoding that information. Okay. All right, so that's basically how in Nengo you would do everything that we've done, so sort of like the initial sort of assignment. I should actually specify a few things. What's going on with these neurons? A couple things. These neurons, a couple important parameters, other than what the leaking, what neuron type there are. A couple other things you always did is you always said, okay, well, what's the range of represented values? And that is in Nengo, that's called the radius parameter. Okay, and we can sort of see, well, let's say I change this input to, I don't know, 2 times the sine wave. So the default radius is 1. If I change my input to 2 times the sine wave, now you can see, okay, look, my black line, that's my input. The neurons are not good at representing values outside of the range -1 to 1, so they're doing a bad job at that. Okay. If I want to adjust the radius of my neurons, then I say, all right, radius is 2. And now they're fine between -2 and 2. Another thing that we saw in the course is a lot of times, so where did the gains and biases come from? So for that in the course, we would do things like, okay, we would randomly generate intercept values and maximum firing rates. There is a default for that. You can either specify a big long list of numbers there for what you want the intercepts of individual neurons to be, or you can specify one of these uniform distribution objects. So that's saying, hey, for each neuron, randomly generate an intercept between -1 and 1, which is the default. And for the maximum rates, it's uniform between 200 and 400. Whoops, max rates, plural. Okay, so that should be exactly the same. But then I could do something like, I don't know, maybe I want really, really low firing neurons, so between 20 hertz and 40 hertz. Oh, much lower firing rate, we get some more noise, but the system still works. Okay. So those are the same sorts of things that you would normally specify, or that you've been doing in your courses, in the assignments. I guess there's one other really important thing. I haven't shown how to connect groups of neurons together. Let's do that. First of all, I'll put this back up to reasonable numbers. So I'm going to make another ensemble. I don't know, another 100 neurons. Dimensions is 1. And I might do a connection from A to B. Okay, so we did these connection things. You could connect from a node, one of these things that's some arbitrary function, to an A. We're going to use the same sort of syntax to go from A to B. Again, there's going to be a default synapse when you make that connection. So it will automatically put in a 5 millisecond one there if you don't specify anything. So I'm just, we'll leave it in there just for clarity. And now I should probably actually record data from that. Probe B. Probe B. There we are. It's going to run. That's plotting A. Sure, and then we can plot on top of that what is B doing. Okay. So again, let's maybe make that a little bigger. Okay. So the black line is the input, the blue line is what that first population gets, the orange line is the next population. Of course, that next population, I didn't change its radius. So let's go back and simplify all this back down to a radius of 1, and a sine wave of amplitude 1. Yay. We've got all things. Yep. So the blue line and the orange line are basically on top of each other, as we would expect. When connecting groups of neurons, the whole point of the previous lecture was sort of saying, hey, you can also approximate other functions. So we can also do that when we specify connections. So let's say, I don't know, let's do this function. Okay, so that's computing the square. When I make the connection, I can say the function is square. Now when it solves for the decoders, when it makes that connection, it's going to go ahead and find decoders that approximate that. If I don't specify a function, it's going to find decoders that approximate the identity function. Okay, so now I can do that. Cool. Feeding in a sine wave, getting out that first population A is this blue line. Second population is computing the square of that. The square of a sine wave is, right there. Yeah. And if you go ahead and do the math, that is the correct sort of math for that. Okay. Awesome. So that's the basic tools that Ningo provides for building up complicated systems. And so far, it's just sort of basically what you're writing for your first, actually up to assignments 2 and 3. So for assignments 1, 2, and 3, you're basically implementing the same functionality that I just showed here. Okay. But Ningo is also set up, and the whole point, the reason that I'm going to went through this whole example is we can use this to do recurrent connections as well. And we're just going to use exactly the same sort of syntax. What do I mean by a recurrent connection? What's going to go on here? All right, let's do a whole new example. Yeah. I can make a new model. Math model. I'm going to make an ensemble. This is 1. And I'm going to have a stimulus that is, say, I don't know, just 0 all the time. Actually, I don't even need to do that in as a stimulus because, hey, if I don't put in an input, then it's going to be getting an input of 0 all the time. But it's perfectly fine syntax-wise for me to define some function, my function, and I don't know, what function am I going to do? I don't know, x plus 1. And I can make a connection from A to A where the function is my function. Okay, this is what I mean about a recurrent connection. What the heck is this system going to do? Okay. And if we sort of, I don't know, stare at that a little bit, it's like it's hard. I don't know if people have intuitions about what that's going to do. In terms of what's going to happen in terms of actually just finding connection weights, we're going to do it's going to find connection weights in the same way that we found connection weights for this feed forward function. We've got some function. It's going to find a decoder that does a good job of taking the activity from this population and decode that out. It's going to multiply that decoder by the encoders from the second population. That's my connection weights. What the hell is going to happen here? Well, let's probe A. Let's go probe A. We should probably put a filter on there. Synapse is sure, but there. Just because we're going to be plotting it. We're going to make my simulator. And, oops. simulator sim.run. I don't know, let's run it for 1 second. What's going to happen? Sim.data A. Okay. The value starts at 0, fine, that kind of makes sense. It shoots up pretty quickly, and it saturates at some value. What does that make some sort of sense? Well, we can sort of vaguely think that this kind of makes sense in that, well, if this is the function being computed and we're connecting from A back to A, well, initially the input to A is nothing, so it's going to be representing 0, fine. But then since it's representing 0, x plus 1 is 1. So this connection is going to be feeding an input value of sort of 1 back into this population. So it's going to increase its value. But of course it can't keep going up to infinity because the neurons are only good at representing values between -1 and 1, so it's going to saturate at some value. Alright, that vaguely makes sense. But like, how do we know how quickly that's happening? Right? Like how do we know how quickly that's going to happen? And how can we adjust that? Well, we can sort of imagine that we can adjust that by changing what this number is that we're adding. Right? If I just added 0.1, no, now it goes up a little bit more slowly. Okay, that kind of makes sense, but how much more slowly? Like, why that much? What else would affect its timing? Well, there's also a synapse on this recurrent connection. Right? And the default is 5 milliseconds. What if we had a longer synapse? What's that going to do? It's going to do something, but what? Right. Much longer synapse. Ooh. Try that again. That. Now it goes up much more slowly. It's going up in a nice, very, very straight line. That's kind of nice. Very, very straight line until we get about to 1, and then it levels off. All right, so again, I'll go back to what it was before, 0.05. So that's this, nice and sharp. With a longer synapse, 50 milliseconds, now it's going up more slowly. So the actual behavior of the system is dependent on both the synapse model and the function that's being computed. This is the sort of thing that we want to get math on in order to really understand. Let's do a little bit more exploration before we get to the math. Fine, that's going to work. What about some other function? What if I do this function? Well, I'll do that. What's it going to do? Oh, well, it's just going to have 0 come out. And that kind of makes sense because I've got no stimulus. All right, so A is something near 0. Something near 0 is being fed, -0, fine, is being fed back to itself. So that's going to be 0, fine, it's going to stay at a value near 0. So let's actually have some sort of stimulus as well. That's just going to be the value 1 all the time. And I'll make a connection from the stimulus to A. Okay, so that's just going to be feeding in the value 1. Now what's it going to do? Well, I'm going to be feeding in a value 1. This population A is getting 2 inputs. It's getting 1 input from the stimulus, and it's also getting an input from this recurrent connection. It's going to start at 0. Like, initially, we're not representing anything, but I'm feeding in a 1. I'm getting a 0 from my recurrent connection. That should mean that the value in A is a 1. But then that's going to mean that the recurrent connection is now going to be feeding back -1. So now my input should be 1s and 0s. So it feels like, at least one thing that sort of feels like is this should like alternate between 0 and 1, something like that. But then there's also the synapse in here. What the hell is that going to do? Again, we can run it and find out. And it sort of did something and then 0.5. Why 0.5? Well, hold on. Oh, hold on a second. If A is currently 0.5 and I'm feeding in a 1, then the actual inputs to A are going to be the 1 coming in from the stimulus. The 0.5 that's currently being represented by A is getting multiplied by -1. And so the total inputs to A are the 1 minus 0.5, which is 0.5. So that means it should be stable at 0.5. So we can kind of understand that it would do that, but what happened here? Why did the dynamics shoot up and then come back down? What's going on? Okay, we can sort of understand that it's going to stabilize at 0.5, but there's other dynamics that are happening here. All right. What else can we do with this? Variety of, yeah, so we could sit here and keep playing around with different functions and whatnot. What I'm hoping to get is that there was some sort of, it would be nice to have some math that would let us understand exactly what this dynamics really is doing. So, we have the simulator let us do things. We would like some math to let us understand what it's actually going to do. So, back to the lecture notes. Right, so here's a bunch of those examples, similar to what I was just looking at. I think those are pretty much the same experiments. Yeah, we can play around with all sorts of different options here. What is going, what can we do to actually make sense of what's going on here? First step, in order to really make sure that we can understand what's going on with this dynamics, is we need to understand the dynamics of the feed-forward version, okay? Which is something that we got mentioned in the previous lectures, but let's really try to nail this down and understand it. In particular, if I've got a connection from one group of neurons to another, and it's just computing the identity function, but there is also a synapse involved in there, then what's the behavior of the system going to be? Okay. And the place that we sort of saw this, yeah, let's go back up to this example. I'm going to have my function be the identity function. Oh, identity function equals identity. And I'm going to just, as my input, it's going to be return 1 if t is greater than, I don't know, 0.5, else 0. Okay. So we're just going to do that function. And we're going to see what that looks like. Let's maybe not run it for quite so long. Let's run it for 1 second. And what we're going to do is we are only really interested in that second population, so let's only plot. Oops. Plot helps if I know how to type. There we are. So the black line is my input. The blue line is what that second population gets. And we've got one filter involved that is sort of the connection between the two. So the connection from A to B has some synapse involved. And then we also have a synapse involved when we are plotting it. Okay. What happens when I make that synapse longer? Something like this. Okay. For some of you, this may jump out as a very common thing that that appears in real physical systems a lot, this is a low-pass filter. And all we're pointing out here is that because of the linearity involved, even though we're applying that low-pass filter, the synapse at the level of individual neurons, the overall effect is, we can sort of imagine it's the same thing as if I had just taken this input stimulus and applied a low-pass filter on it. And we can check that actually by saying, all right, when I probe that stimulus, also put a long filter of whatever, what did I say, 100 milliseconds? I'm going to put the same 100 milliseconds there. Now that black line, that's what the ideal 100 millisecond low-pass filter would do to that input. And what we're seeing here is that that same filter that is happening at the level of neurons is basically, the overall effect is as if we'd taken that filter and applied it to the value itself. What do I really mean by that? So what we're saying there is, if I have some computation being done, whatever that function is that I'm asking the neurons to approximate, I don't get exactly that function. I get that function convolved with a low-pass filter. Okay. Another way to write that is in the feed-forward situation. If I've got some input u, I've got one group of neurons representing u, my output is x, that's my second group of neurons, and I make my connection to approximate some function g, what I'm going to get out of it is x is not going to be exactly equal to that function applied to u. X is going to be that function applied to u convolved with whatever my synaptic filter is. Okay. It's going to be a smooth version. It's going to be a sort of a blurred version of that. It's not going to, if my input changes suddenly, my output is not going to change suddenly. It's going to change smoothly. And that's the sort of the standard way in math of writing that out. If I have a recurrent situation, so that's for if I have some neural representation, so I have some input population representing u, got an output population representing x. When I connect u to x, I get it to approximate the function g, and I have some particular function. That's this thing here. That's the function that you're pasting down whenever a spike happens. So for the simple low-pass filter case, that's the function. I'm flat, and then I spike up, and then I slowly exponentially decay down. Okay. All right, that's the way in math of writing out the feed-forward situation. What's happening in the recurrent situation? Well, in the recurrent situation, I still have this input. I've still got some input that is some function to be approximated on my input. But now I also have some connection from this neuron population that's representing x. I'm computing some function on that, and that's also getting passed through my synapse model. So that's the math that says how will x change when I go ahead and specify these functions. So again, as I was playing around with different functions, really what I was doing is I was changing f. Okay. I could also have been changing this function here, which is whatever function I'm applying to the input. So in general, this is what it's going to look like. And really what we're trying to say in this statement of, well, how will, when I was looking at those weird graphs and saying, whoa, what's it doing? Why is x doing some weird shape? Really what I was trying to say is, well, if I have this math, what does this math say about how x will change in time? And this is initially pretty ugly math. For some people, what do I do with this? Depending on how recently you've taken these sorts of math courses, the answer may or may not be clear. And the main trick is, well, look, convolution is a horrible, horrible operation. Get rid of it. And the standard way of getting rid of convolution is to do either a Fourier transform or a Laplace transform. In this case, the Laplace transform turns out to be really what we want to do. So I'm going to say, all right, I'm just going to write the Laplace transform. Again, depending on how much background you have on Laplace transforms, you're transforming time into some other space, and it's called S, and generally you put things in capital letters. Fine. All right. So that's how we're going to write that out. Why does that help? Well, one thing it does is it turns this convolution into multiplication. Good. So what? Well, it also turns out that that low-pass filter, that exponential decay curve, is one of the things that there's a really nice form for writing the Laplace transform of. It's, you go to the back of your textbook, you take a look for that curve, and it says, oh, this is what the Laplace transform of that curve is, where tau is the time constant of that filter, of that low-pass filter. Okay, now it's just algebra. Now I just do some manipulation, move things around. I'm going to collect things together. I'm going to put Sx of S on one side because it's got a nice inverse Laplace transform. And I'm going to collect together all the things that have to do with x and all the things that have to do with u. And then I'm going to do an inverse Laplace transform. And Sx of S has a nice inverse, which is the derivative. Okay. So this is telling me how will x change over time for a particular function being computed on my recurrent connection and a particular function being computed on my input connection, where tau is my time constant of my low-pass filter. Okay, the time constant of my synapses. So that's actually the math of what is going to happen. If we wanted to sit down and go ahead and figure out, okay, well, what is the slope of this line? We could go ahead and say, oh, yeah, that is following that math. That's exactly what that math is then going to end up telling us is going to happen. And there's one really interesting upshot of this. And that is that since I know this is going to happen, if there's some differential equation that I would like my system to have, then that means I could set the recurrent connection to this, and my feed-forward connection to this, and if I substitute those two things into this thing, then I'll find out that the final behavior is what I want. This is really weird. Again, this sort of, what? What we're saying here is we can use all the same techniques that we were using in order to find connection weights that approximate functions. And now, if I have some differential equation that I would really like my system to approximate, then this is saying, well, what I do is I try to build connection weights that approximate these functions, place them into a system that has a synapse that has some time constant in it, and as a side effect of all of these things, I'm going to end up with a differential equation that I want. Okay. This is giving us new capabilities. All the stuff we've done so far, and indeed all the stuff that people normally do with neural networks, is about approximating functions. And this is saying, if I want to, I can take a differential equation, break it down into functions in this sort of weird way, and then make it such that when I put it back together as a full network, the combination of approximating those functions and the low-pass filters of the individual synapses is going to give me the particular differential equation that I want. Cool. All right, what can I do with that? Lots of different things I can do with that. So one, if people have taken sort of control theory or dynamic system sorts of things, anything that I can write as, like there's a whole field of people doing control theory and systems where they're defining different systems in terms of differential equations, right? Really what we're doing here is instead of saying, okay, building up differential equations based on integrators, we're building up differential equations based on whatever my synaptic filter is. Right? So it's sort of It's just a mapping of that sort of control theory stuff and that sort of systems dynamic stuff, if people are familiar with that. And the mapping for the special case of a synapse being a low-pass filter is really straightforward. And basically all you're doing is scaling the dynamics by whatever by tau,